it's time for the program. And so Ness, how long? Let's see, you've been a club member for about 5 years.
So I came here in 2012 or 2013 for the first time.
Okay.
Yeah.
Okay.
So before I start my talk, I want to tell a little story about that.
Oh, okay.
So
Well,
I might answer any.
anyway, let's welcome.
Hi everyone. So I wanted to tell the story as to why I'm so excited to be here tonight. This is a really special moment for me. And so the story starts when I was little. I didn't want to be an astronomer when I was little. I wanted to be an artist. One of my earliest memories was when my mom taught me how to crochet. And I wasn't very good at it, so I took the yarn and the hook to school, and I would brush through my homework, and then I would sit and I would practice to try to get better. And then a few years after that, I taught myself how to macrame. And I loved crafting. I loved creating things with my hands. A couple years later, after high school, I had saved up money, and I bought a used sewing machine. And it didn't stop there. A couple years later, I learned from someone how to knit. And I wish that I could put all those pieces together and use that as a way to make money. I wanted to be a crafter, an artist, professionally. So in 2010, my partner and I moved out to his mom's fiber farm. Jane kept a flock of sheep. And while I was living there, she showed me how she took care of them. And she taught me how to process the wool and spin it into yarn. And then she taught me how to weave, and she taught me how to felt. She taught me how to do a lot of different things creatively with wool. So she had a fiber art business, and it was very inspiring for me. So the following year, I came back to Columbus, and I took all of these little pieces that I had gathered along the way, and I wrapped them up in that inspiration that I got from watching Jane's life. And I started my own fiber art business. And I loved it. I loved getting up and going to work today because it meant I got to sit on the couch, watch TV, make stuff. It was great. And I had every intention of doing that for the rest of my life. Until one day I couldn't do it anymore. Because I had developed a nerve injury that made me unable to use my hands for more than a few minutes at a time. So I quit creating, and I became very depressed. And so I spent probably a couple of months in bed with Netflix and my self-pity. And then one day, things changed. I stumbled upon this TV show called The Universe. And for those of you that don't already know, The Universe is kind of like Cosmos, but not quite as good. But it's introductory astronomy lessons from professors and astronomers. And these lessons are mixed with beautiful imagery and usually really contrived and silly analogies to help it stick in your head better or something. But I was hooked. I didn't know anything about astronomy, so every little piece I learned was super interesting and I wanted more. So at this time, there were 6 seasons of this show. And when I watched the very last episode, I dragged myself out of bed because what happened at that time was this was the first time in months that I didn't have self-pity as my dominant thing going on in my brain. I was curious and I wanted to learn more. So as that episode ended, I got out of bed, put on some pants, and I drove to Perkins. And I came here to join the Columbus Astronomical Society. So I loved it. CAS has changed my life. And I started coming here. There were a wide variety of lectures to attend, and there were telescope nights. It was very interesting. There were a lot of really cool people to meet. And so I learned that, every time a question was answered with something that I learned here, I had 10 new questions. And so this inspired me to want to try to study astronomy on my own. So I found this platform online called Coursera, and it's free online classes. I signed up for every single astronomy course that they offered. And I waited patiently, the classes started, I went through them, and when I finished them, I signed up for them again. I loved it. I wanted more. And I kept coming to CAS. And then there was a turning point. So some of you might remember this day. This was March 8th of 2014. And I went to a CAS monthly meeting. And the meeting was given by Carl Koger. He was a PhD student of Rick Pogge at the time. And the title of the talk was called The Curious Case of M82. And it was an interesting talk, but the talk went completely over my head. And as I was driving home, I felt a little disappointed. I wished I knew why M82 was curious. But I realized something while I was driving home, that if I wanted to continue to try to peer deeper into the inner workings of the universe, that I was going to need to get a university-level understanding of math and physics. So this motivated me to apply to OSU. A couple months later, they notified me that I was accepted. And the following year, I enrolled with a double major in astronomy and physics. So when I got started, it wasn't very easy. It was pretty bumpy. I hadn't been an official student in quite some time, and I had never taken a physics class before. But I found a rhythm somehow, and I started to do well in my classes. And as an interesting twist of fate, in the summer of 2018, right before the start of my senior year, Rick Pogge took me under his wing as a summer student. So this is the story underneath the research that I want to share with you. But I also wanted to say one more thing before that. So when Karen had reached out to me and asked me if I would give this talk, my first reaction was sheer panic. I was very nervous. But I realized that if I said yes, I would get the opportunity to stand up here and express my gratitude for Perkins Observatory and for the Columbus Astronomical Society, for helping me to find my feet again, and for giving me, for illuminating the pathway to pursuing astronomy in a more professional sense. And it turns out that being an astronomer is super awesome. And the research experience is very similar to making art, I would argue. It's a very creative and satisfying process. And it's a lot of fun to share with other people. So, as you probably read, so my talk is about taking the temperatures of hot gas and star-forming regions. So you might be wondering why we care about temperatures at all. So we care about temperatures because we care what the universe is made of. And if you are trying to count elements in a galaxy somewhere, you need to know the temperature from where you're counting to be able to figure out how many elements there are. This is a rendition of the periodic table that was made by Jennifer Johnson, who's a professor at OSU. The two most common elements that are in the universe today are hydrogen and helium. About 75% of the universe is made of hydrogen, and about 25% is made of helium. The remaining less than 1% is everything else you see on this table. Fun fact, astronomers call these metals. Everything heavier than helium is a metal. I'm going to be talking about metals today, but I'm mostly talking about nitrogen, oxygen, and sulfur. So if you can read this color coding, what we see is that hydrogen and helium were made from the Big Bang. But everything else you see on here was made in the lives and deaths of stars. So astronomers look at galaxies as laboratories to see where the elements are coming from, how they're being created, and how their relative abundances change over time. So how do we take the temperature of something that is millions of light years away from us? We use spectroscopy. Spectroscopy, I will argue, is one of the most versatile tools in the astronomy toolkit. So I'm going to show you how this works. We start with an energy source. This light bulb emits wavelengths across the visible spectrum. And we know this because if we look at the light through a prism, the light is spread into this rainbow. The reason why this happens is because the different colors have different wavelengths. And as you run wavelengths through a prism, the different wavelengths will bend at different angles. So they spread out in such a way. This is called a continuous spectrum. So what happens if we cover this light bulb with a cloud of gas? Well, if we look at the light with the gas in between, we see that we still have our spectrum, but there are specific wavelengths of light that are missing. Interestingly, if we take a spectrum of the gas cloud itself, we find those missing wavelengths. So why is this happening? Well, what's happening is the light is leaving this light bulb, and the light is, there are packets of light called photons. So these photons have different energies, and they're represented with different wavelengths. These energies will interact with the electrons on the elements that are inside the gas cloud. So some of these wavelengths will be absorbed into the gas and will excite the electrons. That's why we call this an absorption spectrum, because those wavelengths have been absorbed, and they're not showing up in our image. But the electrons don't want to be excited. They want to go back to their ground state and be close to the atom. So they de-excite, and they release the same light that they absorbed, they release it back into the gas. So that's why we see these emission lines in our emission spectrum. This image here is the sun's spectrum. It was taken on the Solar Observatory at Kitt Peak near Tucson, Arizona. We can see that our sun emits wavelengths all across the visible spectrum. And we can see that our sun also has absorption lines. This tells us that the outer layers of the sun are cooler than the inner layers. And as the photons leave the sun, they interact with this cooler gas around the outside, and some of the wavelengths get absorbed. Each star has a spectrum, and each spectrum is different. It's sort of like a fingerprint. By looking at these absorption lines, we can learn a lot about what's happening in our sun. We can learn about its composition, we can learn about its temperature, and we can even learn how quickly it's rotating. But to learn about these things, astronomers like to represent the spectrum a little bit differently. They like to plot it as the intensity of the light as a function of its wavelength. You can see that on this spectrum, so this peak is the visible light. And as you go to the blue side, the wavelength gets shorter, and as you go to the red side, the wavelengths are longer. You can see these dips in the spectrum. These are the absorption lines that we saw before. So this image is the MK spectral classification system. So we can use spectra to classify different types of stars. There are O and B stars, which are very big and bright. They emit most of their light in the ultraviolet and lower wavelengths. And these stars live very short lives, burning through their fuel quickly. We have cooler stars like M stars that emit most of their wavelength in the red region. These stars are much cooler, they live a lot longer. And we also have our sun is a G star. So it emits its wavelength spread throughout the visible range. And this is probably why we evolved to have our eyes sensitive to visible light. If we were around a different type of star, our eyes might be more sensitive to different wavelengths. The one thing I wanted to say about this classification system is, so I said it's called the MK system. MK stands for Morgan and Canaan. Now some of you probably already know, Philip Canaan worked at Perkins, taking spectra on photographic glass plates, and he used these spectra to build this system. So that was pretty exciting. This spectrum is of the Crab Nebula. This is a supernova remnant. So this is an example of an emission spectrum. You can see the emission lines from this gas. But we're here to talk about star-forming regions. So I'm going to bring up that image that we looked at earlier. Who knows? Raise your hand if you know what star-forming region this is, or if you've seen it in a telescope. Probably a lot of you. Yeah, this is the Orion Nebula. It's pretty popular. It's relatively easy to observe. And this is a star-forming region. So what happens in star-forming regions is you start with a big cloud of gas. And this gas over time will start to compress on itself as its own gravity pulls it in. And the gas will compress more and more, faster and faster, until it is so tightly compressed and the gas has become so hot that at one point it can sustain nuclear fusion. And at this point, a star is born. And that star will be spinning very quickly. It will be emitting large amounts of ultraviolet light, and it will also be producing quite a bit of wind that will push on the gas and actually blow the gas that it was born from away. So we can see this star right here has cleared all of this gas away. And then we have a couple of stars that are hard to make out right here that have pushed all of this gas. This is another star-forming region. It's NGC 604, and it's one of the largest star-forming regions nearby that we know of. I chose this picture because I wanted to talk to you about the structure of these regions, and I think it's a good example. So you can see the cavity here with our new stars. And this gas that you're looking at is mostly hydrogen. When we look at the structure, we see the stars in the center, and we can see that these stars are emitting wavelengths that are energizing the gas around it. So in this cartoon that I made, I use spectroscopic notation, so I'm going to take a second to explain to you what this is. So the way it works is if you have a neutral atom, you give it a Roman numeral 1 after the abbreviation. So H1 is neutral hydrogen. And for every electron you pull off of your atom, you get another Roman numeral. So sulfur 3 and oxygen 3 have had 2 electrons removed. So we can see that the closer you get to the stars, the less electrons you're going to have. You have more ionization occurring closer to the stars. And we can also assume that you also have a hotter temperature in this area. And as you move out of the region, you have less ionization occurring. Throughout this talk, I will be referring to the star-forming regions as H2 regions. And that's because they're mostly ionized hydrogen, or a group of protons with free electrons whizzing around. That's the structure that we're looking at. This is a spectrum of a star-forming region. You can see that where the spectrum was taken, we have a star and we have gas around it. So when you look at the spectrum, you have both an absorption spectrum and an emission spectrum on top of each other. Let me zoom into this so you can see it better. So these wavelengths here, this continuum, is mostly from the underlying stellar population. If you remember the MK system I just had up, when I pointed out the O and B stars, a lot of the light was coming from the ultraviolet region. We see that here in our H2 regions. We can look at this continuum and say that the stars that are ionizing this gas are mostly O and B stars. But we want to know about what's going on within the gas cloud. We want to know about the gas. So we're going to look at these emission lines that the gas is creating. So there are 2 processes that create emission lines. One is called recombination. So in recombination, you have a free electron that directly recombines into an ion. It will emit different wavelengths. It will emit any wavelength that it wants to get it from its moving state to its stable state once it picks the state that it goes into. That's called a continuum photon. So they can be any wavelength at all that you see. And then, as the electron goes closer and closer to the atom, you have specific energy levels that have a specific energy between them, which creates an emission line that has a specific wavelength. So these big bright lines are emission lines from that process. So you'll notice that I've highlighted the hydrogen and helium lines in this spectrum. There are also metal recombination lines, but we won't see them here. And the reason why is because the strength of these lines is dependent on how many times this interaction is happening. And for every 1,000 hydrogen atoms, we have only 1 atom of a metal. So they're very rare. These lines will be 1,000 times smaller, and at that point, you wouldn't be able to say if you're measuring a line or noise in your signal. So if we want to know what's happening with our metal lines and our metal atoms, we need to find a different process that creates them. And this is called collisional excitation. So collisional excitation occurs when you have a free electron and it's flying by and it collides with an atom and bounces off. And in this process, it imparts some of its energy to that atom. And so one of the electrons on the atom becomes excited. It doesn't want to be, so it de-excites, and it releases an emission line with a specific wavelength. So I've highlighted some of the common collisional excitation lines that we see from our metals. So we want to measure electron temperatures. We rely on these very faint emission lines to do so. Even with the collisional excitation lines, these lines are very small. So before I said that we can find these more highly ionized atoms closer into the stars. We expect that our region has different temperatures, so we use the presence of different lines to measure the temperatures throughout the region. So we look for O3 lines to tell us the hotter temperature of the region that's closer to the stars. We measure sulfur 3 lines to learn about the intermediate region, where it's like not too hot, not too cold. And we measure nitrogen 2 and oxygen 2 lines to tell us about the cooler areas of the H2 region. So we know measuring ion temperatures from collisional excitation image lines is hard. Measuring them from recombination lines is even harder. But thankfully, we have a super awesome team to tackle these problems. And I'm super excited to introduce you to the CHAOS team. CHAOS stands for the Chemical Abundances of Spirals. CHAOS is led by Rick Pogge at OSU and by Evan Skillman at the University of Minnesota. And as Rick said to me, the 2 people on the left get all the money, and the 6 people on the right do all the work. So CHAOS's main goal is to look at nearby bright spiral galaxies and to measure the abundance of elements throughout the galaxy. They like to compare the relative abundances, so how much oxygen do you have with how much nitrogen. And they like to do so by making measurements closer into the center of the galaxy to farther out. This is called an abundance gradient. This is their main goal of the project. CHAOS uses the Large Binocular Telescope, or LBT, to get their data. The Large Binocular Telescope is located on Mount Graham near Tucson, Arizona, and it has 2 8.4 meter mirrors that are mounted together on a single mount. So I know 8.4 meters is big, but if you asked me to go run a circle in the parking lot to show you how big, I probably wouldn't be able to do it. I don't know 8.4 meters well enough. So I was really surprised because a couple of weeks ago, I was remote observing at LBT, at Stewart Observatory, and I found this picture on the wall. This is a big telescope. There are 60 plus or minus 1 to 2 people in this picture. This is the Stewart Observatory Mirror Lab staff, and they're surrounding just one of these 2 mirrors. Because we have 2 mirrors that are mounted together, if you take the entire light gathering power of this telescope, you're left with an 11.8 meter mirror. That makes this the largest optical telescope in the world. Also, one cool feature about LBT is if you just want to resolve something, you can put it in interferometry mode. Because the mirrors are separated, they have the resolving power of a 22.8 meter telescope. So this is a remarkable instrument. CHAOS uses the multi-object double spectrographs. These are spectrographs that are located one behind each of the 2 mirrors on LBT. And MODS was built at OSU in the basement of the astronomy building of McPherson Chemical Laboratory. And I put this picture originally up to show you how big the spectrograph is. But I also have to say, these OSU fans will use literally anything with the OHIO arms, even a scarlet and gray spectrograph. So I know you already saw this picture, but I wanted to point it out again. This is the Crab Nebula, and the reason why this is a wonderful spectrum is because it was the very first spectrum that MODS imaged with both spectrographs in operation together. So this was their first light. Oh, the other thing I want to point out is the way that MODS works is a medium resolution spectrograph, but it has very wide wavelength coverage. So it goes from 3,200 angstroms to 10,000 angstroms. And what that means is it takes the entire visible spectrum, and then it also grabs some ultraviolet light and some infrared light, which is really great for measuring emission lines because it can grab lines that are very far apart from each other. So you get a lot more information about what's going on in your region. These are a couple of the galaxies that we've worked with. So far, CHAOS has taken spectra of over 500 H2 regions in 5 galaxies. So these are a few of them. And the lines that you see here are slit locations. So what this is doing is this is marking the H2 regions in the galaxies. Once we know where they are and where we want to get the light from, we make a mask. And the mask goes on the spectrograph, and it pulls in light from multiple regions at once. So you can do one exposure and get a whole bunch of spectra, usually around 25 at a time. You'll see that some of the holes are squares. Those are not for H2 regions. Those are for guide stars. Because it's challenging to line this up with very faint H2 regions, you don't want to put it in the wrong position. So you find your guide stars and line those up, and then the masks are hopefully in the right place. So after the exposure, we get something like this. And so these are all different spectra from different H2 regions. And I wanted to point out that without doing any processing whatsoever, we can already see the signature of certain lines that we care about. And we can also see variation between the spectra. We see metal signals that are highlighted, but we don't see these signals down here as bright or at all. But yet you can see this hydrogen line throughout. All right, so back to ion temperatures. So I already showed this slide, but I wanted to remind you. So we are looking for these ion temperatures. We expect that if I measure a temperature from O3 and if I measure a temperature from N2, I don't expect them to be the same. One is the high temperature region, one is low temperature region. So although we expect them to be different, we also expect them to be related. If I have a very hot H2 region, I expect that the low temperature is going to be higher than what I usually see. So what you see here these are different temperatures, different ion temperatures. So we have nitrogen 2 temperatures, and we compare them with sulfur 3 temperatures. Now, if these temperatures were all the same, these plots would be x equals y lines. They would be just perfectly straight lines, or slope 1 lines. And what we see is they're not, and we don't want them to be. But we do see that these data points, they have relationships with each other. And this is very helpful. We like this feature because if I want to know the amount of sulfur in an H2 region, but I can't find any sulfur lines because they're too small or maybe my spectrum is too noisy, then I can measure some other lines, find some other temperatures, put them in the equation that these relations represent, and I can pull out the sulfur 3 temperature so that I can estimate how much sulfur I have. So these relationships were really helpful. I'll just quickly mention that this blue dotted line was relationships that were put in place in '92 that were based on theoretical models. And then in early 2000s, Chaos had revised these relationships by using very carefully measured empirical data. So that's why those lines are slightly different. So this leaves us with a question. What is the best temperature? So I want to draw your attention to this point up here. If you look at that point, your nitrogen temperature is telling you that your sulfur temperature is way too high. But if you talk to your sulfur temperature, it tells you that your nitrogen temperature is way too low. So who do we believe? Which temperature wins? We don't know. We don't have a tiebreaker. We don't have a way to identify what the best temperature is. And this can cause a problem. We want our results to make sense. We want to be able to understand them. So the question is, how do we deal with discrepancies? So I'm going to give you a moment to appreciate this amazing meme I made to motivate my work. All right, so how do we deal? So how do we deal with our ionized hydrogen cloud discrepancies? Well, we want to measure an average temperature of the entire region, because then we'll know that the temperature that we trust will hopefully be closer to that average, and we can give it more weight. So what I've been working on is wondering if we can measure the temperature using the hydrogen spectrum. Now, why hydrogen? Well, hydrogen because the entire region is made up of hydrogen, and it's doing reactions all the time. It's having electrons recombine. There are tons of hydrogen recombination lines. So how can we use those? So I've been looking at the hydrogen Balmer spectrum. These are spectral features that are produced when an electron goes into the n equals 2 state. These features are both emission lines and continuum. So probably the most common, well-known hydrogen line, Balmer line, is the H alpha line. So this line is produced when you go from n equals 3 to n equals 2. And then we have H beta, which is from n equals 4 to n equals 2. We have H gamma from n equals 5. And we also have H delta, H epsilon, H theta. And then we give up on the Greek alphabet. And we just start numbering them, 7, 8, 9, 10. And they would go all the way to infinity. What I wanted to point out is the larger the jump, the bluer the line. So as we increase from higher and higher levels, our line gets bluer, which means it's more energetic. And you might also notice, I can pull up these other lines, that the distance between them gets smaller. They get closer and closer together. These lines pile up as they approach 3646 angstroms. So what's so special about 3646 angstroms? Well, if I had a hydrogen atom right here and it had an electron in the second state, and I reach in and I pull this electron off, and I pull it off just enough so that when I let go, it doesn't have any extra energy. It's not going to fly away. I just barely pull it off. The energy that I used to pull that electron off corresponds with a wavelength of 3646 angstroms. If I take this electron and I pull it off, but I pull it hard enough that it can fly away when I release it, then I've used an energy that corresponds with a wavelength shorter than 3646 angstroms. So if we look at this in the other way, when we have free electrons flying around our nebula and they recombine directly into n equals 2, that continuum photon that's released can have any energy it wants to, so long as it's less than or equal to 3646 angstroms. And we call this the Balmer continuum because it has a continuous range of wavelengths. So you can see that our Balmer lines come in, they pile up, they start to become indistinguishable from one another. One time I zoomed in and I was able to get to H23, I think, and then, or maybe 28, but then I couldn't go any further. So if we want to know the value of the continuum, we try to measure the Balmer jump. So the Balmer jump is going to be this continuum here, subtracting off the continuum that we had in the first place. This is probably one of the trickiest parts of this measurement because we have all of these Balmer lines in our way that are piling up on top of each other, and we have to say something about what the continuum is doing underneath those. So if we take the ratio of the Balmer jump and a Balmer line, we can learn about the average kinetic energy of the region, which tells us the average temperature of the region. The larger the Balmer jump ratio, the cooler the temperature. And the reason why this is imagine that you're a proton just hanging out and you want to catch an electron. Well, if you're in a really hot room, those electrons are going to be flying around so quickly, it's going to be really hard to catch them. That's what happens in our H2 regions. In the cooler regions, we have slower moving electrons that come in close to the proton and they recombine much easier. Okay, so how do we turn this Balmer jump ratio into a temperature? This is where cloudy models come in. Cloudy is a photoionization modeling software. And what it does is we feed it some input. We tell it what the H2 region is made of, how old the stars are, and what the range of ionization that we will allow for this specific region. We give it these parameters, and Cloudy does all the physics for us. Cloudy runs physics equations and evaluates what the different features would look like given these conditions, and what the temperature would be, the average temperature, given a specific Balmer jump ratio. So we're left with basically a list of Balmer jump ratios and a list of temperatures. So we plot it as a graph just so we can look at it. It looks nice. And you can use this graph to measure temperature. You can measure the Balmer jump ratio, and then you can draw a line and read it off, and you can say what your temperature is. But because I'm doing this hundreds of times, I don't want to use this graph every time. So what I do is I find the best fit line that can put an equation to these points. So we find an equation to describe this relationship. So here is my equation. Now, I decorated it a bit because I wanted it to look a little less scary. But I want to point out how amazing this is. Let's take a step back. So we have this very tiny spectral feature in a very small amount of light that has been flying through space for tens of millions of years. And we caught it. And we get to make a measurement of that. And we get to put it in my equation. And it tells us the temperature. That's amazing. I love that. Science is great. And this is spectroscopy. This is why spectroscopy is such a powerful tool. Okay, so before I tell you the results using my wonderful equation, I want to give you a day in the life of doing research at OSU. So we start off with this plan. The plan is we have a large number of spectra to go through, and we sort them. So we have our primary sample, which looks so nice. You just want to make measurements. Just can't help it. It looks so great. And then we have a secondary category that has Balmer features that you can see, but there's some noise there. So any measurement that I take is going to be a little less certain than one that I made on the spectra above. So this is my secondary. And then we have this triage set. Now, this is probably the best looking one of all the ones I triaged. But the triage set are spectra that I'm just going to put away and not touch anymore because I wouldn't be able to trust those measurements. Either the Balmer jump is non-existent or the noise is so high that I wouldn't be able to trust a measurement because it could be predominantly noise. So we just leave those alone. So when I started, I went through all of my spectra and I put them in categories. I had my really nice ones, I had my noisy ones. I had some that were like sloping down and some that were going up and down that I didn't really know what to do with. And then I had stuff like this that I just wanted to run away screaming. So once I had my classification system, it was time to plot them and start getting a feel for what they looked like and how this was going to work. So this plot shows the observed spectrum in black. So this is what we got with our stellar component and our gas together. This purple line is the modeled stellar population. So this is done using starlight modeling code, which guesses as to what the stars are doing underneath that spectrum, and then we can subtract them off and just get our nebular component, just get the gas. So something didn't look right to me. And what happened was every single one of my H2 regions was telling me that they were producing negative counts of light. This is physically impossible. So I knew there was a problem somewhere, and it actually took quite a bit of time trying to problem solve this particular issue. So I went into the modeling code. Most of this is still a mystery to me. We looked at it for a long time, but I eventually figured out what I needed to change to get my models to fit the data and to look the way they were supposed to look. Once we got our models much better, then it was time to actually make the measurements. So to make the measurements, I had to fit lines to the blue and red side that would represent the continuum. I had 6 different methods that I started with, doing the measurement a little bit differently each time. And I took these to my advisors, and they suggested that I do more methods. So we did more methods. And at this point, we were starting to see which lines didn't look the way that you think your continuum should go. We were able to make some guesses about how our methods were working. But it was still just guesses. If I had a difficult morning, I might be more pessimistic about what my result looked like. So we started adding in statistical analysis techniques so that we could actually put a numerical value to the quality of our measurement. And that really started to change the process for us. Every time I made a change to my code or my method, I would take it back to my advisors, and we would meet and we would talk about what we were seeing. This entire process was super iterative, and it was really great to be able to get so much feedback and interaction with my advisors the whole time. Oops, sorry. Okay, so then we spent most of the bulk of our time talking about the tiny details. We had to figure out how each measurement that we made would introduce uncertainty in the values, and we needed to give a quantity to that uncertainty. We also needed to account for small details like reddening. So whenever you take a spectrum, there's dust in between you and your light source, and every time your light interacts with dust, it gets sort of bent a little bit and gets a redder wavelength than what it should. Every time we had a little detail like this to think about, I would usually have to go back through academic papers and see how someone else had dealt with this problem in the past, so that I had a pathway to move forward. Sometimes, though, it would involve me learning a previously unfamiliar code like IDL or something, just to figure out what to do next. Ever since I started doing research, my computer has looked like this. But unfortunately, I usually don't have as many cartoons of H2 regions or llamas. Once I got everything sorted and could move forward, it was time to write the thesis. Everything is an adventure in astronomy, even writing your thesis. You don't just write it with Microsoft Word. You use LaTeX, which is like a word editor that you code. And so you write your paper and then you put some code in. And then you write your paper some more and you put some more code in. You need a new paragraph, put some code in. And then when you're done, you compile your paper to see what it looks like. It becomes more fun the more times you use it. I like it. So once I had my draft, I gave it to my advisor. And when I got it back, it had a lot of red ink on it. I also got comments from my daughter. Hers were a lot cuter. All right, so now it's time for results. So we ran our Balmer-Jump ratios through our equation, and this is what we found. So remember the temperature plots that I showed you earlier. This time I'm taking my temperatures here, and I'm comparing them with each of the different ion temperatures from the chaos data set of the same regions. And the most exciting part for me was to see that my average temperatures correlated best with the sulfur-3 temperature across the entire range of temperatures that we see. The reason why this is exciting was it was sort of a sanity check for me. If someone had asked, which is the better average temperature, the hot, intermediate, or low ionization zone, I would hope that my results would look like the intermediate ionization zone, and they did. So that was a good first step. So we were really happy to see this. We also found that we had general agreement with nitrogen too, especially at lower temperatures. And we also found that the O3 is a mess. And we would not want to trust this relationship with any weight because there's a lot of messiness going on there. So we can use these results to further support the work that chaos has been doing. We now have a relationship that connects our nebular temperature to our ion temperatures. So before we were using these collisional excitation lines, and now we have a way to measure temperature with the recombination lines, which are much easier to measure. And another important result was that historically, if you ask an astronomer which temperature would they use to tell you the temperature of their star-forming region, they would all say O3. But as chaos has been working on this problem, chaos has found that sulfur-3 has been a more robust and resilient temperature every time. It's always been more trustworthy for them. So for us to find that the average temperature of the region and the sulfur-3 temperature go hand in hand, that gives more weight to the sulfur-3 temperature. And this gives us a way to answer that question I asked earlier, what's the best temperature? So we would say that sulfur-3 is. Thank you so much for listening to my thesis. Does anyone have any questions?
Where do you go from here?
So we're actually getting more H2 regions from M33. And so I will be furthering this data set and seeing, so some of the questions I have, I would like to explore more galaxies, and I'd like to see if you compare these relationships galaxy specific, would they be the same? So would M33 have these same slopes on their lines as M101? This is actually my undergrad research. So I'm working on different projects as a grad student. So this is, I'm still going to keep this in my back pocket though, because I love working with Rick, and this project is really great.
So, I mean, these are all like extragalactic. So these are all the galaxies. So have you looked at like our local own little Milky Way and see, in the star-forming regions of our own galaxy, what do you find, or have you even looked into that?
Yeah, so I haven't looked into that, and I'm not sure. I think there's an issue with dust and having difficulty looking at the spectra because of the dust in the Milky Way, but I'm not sure about that. I wouldn't be the person to ask, but I think I've heard my advisors talking about it. But I would be very curious to see. I'm sure that there would be a different procedure for, like, you'd have to use a different model maybe, and maybe a different equation. But yeah, I'd be curious to see what the temperatures are.
Because I mean, there's a ton of, hydrogen alpha and hydrogen 2 regions, off the plane, right? I mean, not just looking into within our own Milky Way.
Yeah.
So I was just curious to see if that was actually part of the research that's
Yeah, we haven't done that, so I know that Chaos focuses on nearby but extragalactic. So yeah, I think it just hasn't been part of our data set.
All right.
I'd be curious to learn
Yes.
more about it.
So by that same, so you're looking at face-on spirals. I think that the examples you gave were,
Yeah.
so you wouldn't look at like the Sombrero galaxy or something.
So the trouble with that
There's too
is
much dust, right?
there's a lot of dust, but then also when you have the face-on galaxy, you can be a lot more certain about what you're actually taking a spectrum of.
Oh, right.
And so if it's flat, it would be really hard to isolate one specific H2 region. So
Period
I don't
too.
know that you could trust your results as much or tease them apart. Yeah.
At the point of the basal jump on that graph right there, is there any correlation between temperature and age of specific types of stars that are the same, or regions themselves? Can you extrapolate back to a duration or the length of what's been going on there
Yeah.
with the temperature? Given two specific same stars within that region that have formed, can you determine by temperature what the age of the object is? Is there a lineal path where you know the age by temperature, is what I'm trying to say, I guess.
Yeah, so I don't know about if you have two different age stars within a region. I'm not sure about that, but I do know that you can date an H2 region. And this is based on how far the gas has been separated from the stars, and I don't know what the temperature component is of that, but I know that as H2 regions have a finite lifespan, and as they get older, they get much cooler, and your gas is much farther away, and it's much less ionized, so you probably use different line measurements to study an older H2 region. Yeah.
Yeah, is the continuum spectrum that you subtract out, is that empirically derived by taking measurements of the galaxy, or is that just a mathematical model assuming a galaxy that has a certain population of stars and that kind of thing?
Yeah, so it's even less than that. So what they do, because it's a composite of, we don't know exactly which stars are there or how many. So the fitting method, you give it windows. So this is part of why I had that issue for a long time, was the person who reduced the data had missed an emission line. So let me see, I don't know where, oh wait, it was right here. So so let me try to answer this question first. So what you do is you feed starlight different windows where you don't see any emission lines. And you say, so right here there's no emission line. And this is an absorption line, and right here there's no emission line. And you go through and you give it specific windows to your spectrum. And then starlight goes and runs, it has grids, so it will have many different populations of stars. It will do one type at a time of common stellar spectra. And it runs these through, and it might find a star that has this feature. So we talked about the O and B stars being in here. So the O stars have this. This is a signature O star jump. And B stars are more slanted this way. So it will sort of extrapolate between them. It knows there's an O star and thinks there's a B star. So it will go between, and it will just keep iterating through these grids until it has its best fit. So it will look at the residuals when you subtract them off, and the closest to zero that you get, that's the model that it gives you.
So basically, you're just sampling the in-between areas and then
Mhm.
making a best fit based on that. And then,
Yeah.
and then you know that the stuff that's on the left side of the Balmer jump is going to have these sort of these characteristic features, and then you create a model based on that.
Yes.
Okay, and then you
So,
sample it.
so what we found, so you see how this stellar model is bad.
Yeah.
We don't want to use this. This continuum should never be above what we measure. What had happened when I found where the masks were located, this emission line was not being removed. So we were telling Starlight to give us a model of a star that had this emission line. And stars don't have emission lines like
Yeah.
that. So that's why the continuum was being pulled up over here, because it was trying to fit for this.
Right.
And so once we replaced the masks, I don't actually have this particular spectrum where I would show it, but once we put the correct masks in, then we got that continuum down. And it's not perfect. You'll see that there will be sometimes, like this stellar component is slightly higher than the continuum. There will be some parts that aren't great. So that's another thing that we wanted to explore. Previous work that has used this method for not stellar populations, not H2 regions, but for other things like planetary nebulae. These methods were done with other astronomers. They were modeling the stellar population and the nebular continuum differently. And because we use this modeling process, we introduce uncertainty in our measurements. By assuming that the stars are doing this, we're introducing uncertainty. So we could go in and learn a different way to model the stellar population to remove that component. I hope I answered that.
Okay, yeah, that makes sense.
Yeah.
More technical question, did they ever let you put a couple of eyepieces in that large binocular?
No. Rick Pogge likes to tell us how much it costs per second and per day to use that. I know it's $90,000 a day. I don't remember how much per second. It's a very expensive instrument to use. Yeah.
I noticed, these galaxies are all fairly close, they're thousands of light years. I mean, you know what the limits are? Could you go out millions of light years, or does it, because of both distance, redshift, dust, whatever?
Yeah, so the only exposure I have to this is just this one research project, so I'm not sure. Yeah, I really don't know, I'm sorry. Yeah.
But it was time to reason, I mean, the further away, the more noise you actually acquire. The further away, there's more stuff.
There's more stuff, there's more uncertainty, you have to expose for longer. There's a lot of components.
Well, I think, let's thank Ness again. If you have more questions. I think it might be clear outside.